I'm just going, I know you've seen this, but I'll just quickly repeat. So we've got rainy season from June to October. The main problems we have here, well, we've got a fertile soil, so the main problems we have are periodical drought, water stress, periodical water excess, because you've seen, well, the rains have been a bit not very typical lately, but normally it rains in the afternoon and we have very heavy storms, so a lot of rain, very concentrated, and then drought periods in between. We've got a lot of erosion, we depend on the rain for agriculture, and yields are in general low. These are the treatments we have in the experiment D5. I don't know if you recall, there is a long-term experiment that we have here. Okay, so they're divided in two groups. We have a zero tillage group and a conventional tillage group, divided in keeping the residue, removing the residue 2 times. And we've got 4 rotations. We've got maize, maize, wheat, maize, wheat, and wheat, maize. Where in the zero tillage treatments, we've got some in-between treatments with partial residue retention. Okay, now I'm going to give you 2 presentations. The first one, this one is about comparing growth curves in the time. So the question is whether different management induces a different crop development in time. So what we normally do in agronomical evaluation, we've got one measurement at the end of the season, our yield measurement, that is the integrated value of all that happened during the season. Now, if you've got yield differences at the end, it's hard to know where those differences come from. So that therefore we wanted to have some way to follow crop development over time to be able to tell when the differences occur. Okay, do you get the general idea? So, I'll take you to the field before midday, and then we will measure a bit with the sensor so that you can really see how it works. To follow crop development in time, we generally take 2 measurements per experimental plot. That's what you see here. We just measure the 2 central rows where we later also do this in the same area. We measure yields to be able to correlate the 2. Okay, the first year we did this was in 2003. That was the tryout year, and then we took 9 measurements over the season. And these are the results for wheat. This is only conventional tillage keep and zero tillage keep. The zero tillage are the pink ones, the conventional tillage are the blue ones. And what you see is, this is the line that goes to the zero tillage treatment, that at the beginning of the season, we've got lower NDVI values in the zero tillage and the conservation agriculture treatment. In the middle of the season, they get together, and then the zero tillage treatment stays green a little longer. Then we correlated all the NDVI measurements to the final yield, one by one. Okay, what do you see? What do you read from this table? Okay, we did the same for maize. Here you have zero tillage keep, conventional tillage keep, and this one, the blue one, is zero tillage remove. Okay, so we see for maize the same thing, basically, that the zero tillage keep treatment has lower values at the beginning of the season, they get together. And this is the zero tillage remove treatment. Do you recall what kind of yields you had? I think Brahma showed you real yield results. If you would say between conventional tillage keep, zero tillage remove, how are your yields? I'm not asking for tons per month, just yeah, so if you remove the residue, you've got very low yields, and you see that along the season you've got also very low NDVI values. Now, these are the correlations that we got out of this earlier in the season. And what we see is, again, the non-significant at the beginning, then you get significant correlations, and then non-significant correlations. Now, these correlations are pretty poor, no? 0.5, that's not what we do. If you look at the wheat, we're going into 0.87. That's because in 2003 we had rainfall at a moment in the season where it was a lot of disease, so we had T5 was very heavily infected by a disease, so the treatments that were doing very well were heavily infected, so they had a low final yield. So the ones that had a high NDVI get low final yields, so we have low correlations of yield. So this is a bit, again, this is a PCA analysis with here the initial growing stage values and the late growing stage values. And what do you see from this one? If you think of the graphs that I showed you also. It's actually indicated in blue. What do you see for conventional tillage? Here the conventional tillage has, as I said, high initial stage values, if you look at the graph again. So your conventional tillage has higher initial stage values and lower end of stage values because your development is a bit more advanced in time, so you get ripening a bit sooner, maturity a bit sooner. And for the zero tillage, you get zero tillage with residue has got lower initial stage values and higher pH stage values. And of course, the zero tillage without residue is just low over time. Now, those were some interesting results. What we did in 2004, 5, and 6 was doing more intensive following up of crop development in time. We did 2 or 3 measurements a week with the sensor in almost all the treatments in D5. So this is what we get for maize in 2004. So, okay, you've got development of green biomass, leaves, and here you've got canopy closure, so there you don't get any extra canopy development. You see around 50 days. Here you've got this stable phase, and here we start decreasing, and we'll see in a moment why that is. And again, of course, the gray lines, the conventional ones, yeah, they take off faster, but here around day 60 everything comes together, apart from what we said, zero tillage removal. Okay, this is for wheat. What do you see? In wheat, differences are always less clear, so we've got again the gray lines conventional tillage, the black ones zero tillage. Okay, so we see again higher values at the beginning of the season for conventional tillage. They come together, and which one drops out? Zero tillage. But if you recall, in maize we had 2, no? Yes. Monoculture and rotation. Which one do we have here? Yeah, only the rotation one. I don't know if you recall it from the yield and soil quality results that Ron showed you, that wheat after wheat, zero tillage remove is doing a bit better than when you rotate it with maize. Okay. Now this is 2006. Again, it's a bit always the same, so you can just. So I'll just help you a bit. We see again faster growth. Conventional tillage at the beginning of the season, they get together, 2 drop out, it's maize, so those are zero tillage remove, rotation and monoculture. Now here in 2006 we did 3 measurements a week, so this is a bit more detailed curve, and you can see something interesting around here, day 40, this is around day 8 where you've got a general dip, if you see how it. This is the same for wheat. It's again the same as for maize, just differences are smaller. Now, to look more into detail at the curves, we did soil moisture measurements to see if we could correlate NDVI to soil moisture. And we did that 2 times a week, and this is a graph where you have NDVI and soil moisture. These are the NDVI curves, and this is soil moisture. Now this one is a very interesting one. It's from 2004 in maize. We've got zero tillage keep and conventional tillage keep. And you see again the same story. Conventional tillage at the beginning of the season, if you go out in the field now, it will look just a little bit better, bigger, greener, because they come out a little faster. They come together, and now the interesting thing is this. Here, what happens here? Climate-wise? Yeah, we've got a drought period. Beginning of the season, lots of rain, so all your treatments are happy. Here we've got a drop in the soil moisture, and you see that the zero tillage keep curve that was below the conventional tillage one the whole time flips over at this point and becomes higher than the conventional tillage treatment. Now this is testing, this is just the beginning of filling, it's R1. We have a graph here. This is what happens when you've got moisture stress in different development stages of maize. Now this is the stage where we had that drought period. So that is crucial. That's a crucial period for your plant development. And if you have moisture stress in that phase, you will see it at the end in your yields. Now, this is for wheat. So this goes half a ton of yield difference at the end of the season. Now, if you just have your end of season yield results, you will never know where exactly it happens. Well, you can guess, of course, from your soil moisture curve, but the sensor gives you the possibility to follow up during the season, and then at the end of the season with your yield results, look where is the cause of your yield difference. Okay, that was for maize. This is for wheat, and we see the same. This is the same drought period, and here it was a little later, after flowering. You see again that the black curve flips over the gray one. So zero tillage becomes higher than conventional tillage. Okay, this is zero tillage compared to zero tillage remove again for maize. Now we had these very low curves comparing to the NDVI of the other ones. Here zero tillage keep. Now look at the soil moisture. What do you see? This is permanent wilting point. This was the same for wheat. You can see the same results. Now this is for 2006, and remember that we saw in the curve those dips around day 40 and around day 80. And here you see this is conventional tillage, permanent beds, and zero tillage, all keeping the residue. And you see here our beautiful moisture dips around that time. And this is again for maize, all zero tillage, but with different residue treatments. We've got keep, the same triangle as always, remove the black ones, and the crosses are the partial residue retention. And what you see is that the partial residue retention here was actually even better than zero tillage, keeping all the residue. Okay, so before we just looked at our end of season yield results, and now we have the possibility to follow up crop development throughout the season. These different curves for different management practices show us that we've got a different crop development in time for different management practices, and that might have implications for fertilizer, for all sorts of things, how you will apply your inputs. So you can link these crop developments to all kinds of theories. I don't know what you're all researching, but you can just think about how to apply it in your own fields. And correlated with the limiting factors, what I've showed you was for soil moisture. You can, of course, do it for fertilizer, for insects, for whatever you like. Okay, then what we've done now is we have taken our NDVI measurements in our plot, and then we have calculated the average NDVI value for each plot, and then at the treatment level. Now what you can do also is look at your spatial variability within your plot, so the coefficient of variation of your NDVI. Now from the same measurements, all the measurements we've taken, we calculated the coefficient of variation of the NDVI within the plot. And you can make the same graphs out of that, of course. Now why did we do that? I think you'll just stay long enough to see it in the field. This is D5. This is plot 18. That's zero tillage, keeping all the residue. We've got plot 17 right next to it. Zero tillage, removing all the residue. Now, if you look at the keeping all the residue, we've got the uniform crop performance more or less throughout the field. While if you look at your zero tillage without residue, we've got variability in the field. So, starting to think from that, we started looking at within plot variability. Now, of course, first you have to ask yourself the question that was before the sensor, how are we going to measure this? We can measure plant height, but the problem with plant height is, firstly, it doesn't take that much time to come to a lot of points in one plot, and that the correlation with final yield is not very high. So then we did it with chlorophyll measurements with the stop. Now we've got 64 plots in D5. Imagine yourself running around with a chlorophyll meter, trying to measure enough points to be able to tell something about spatial variability on a plot level. We tried, but it didn't go very well. So the advantage you have with the NDVI sensor is that you can measure a lot of points in a relatively short time, and that you can take measurements along one line, so you don't have any dispersed measurements. Okay. Now, a bit more, this is what you see. Maize, wheat, zero tillage remove. Maize, wheat, zero tillage. This is partial treatment, partial residualization. That was what we saw in the field. This is an NDVI measurement in black, and this is visual scoring. So what you see is that with the NDVI sensor, you have more detailed measurements. The same for the zero tillage remove treatment. In the NDVI measurement, you see kind of gradual gradient, while in your physical scoring, you don't have that much detail. And we can do the same for maize, of course. Zero tillage keep it uniform. Zero tillage remove. We've got a clear trend from one end of the plot to the other. Okay, and these are then the results. Coefficient of variation in function of days after sowing. What do you see from this? The gray lines, black lines seems a bit have disappeared, so it's a bit harder. We've got planting, and then you've got, imagine you have a row, and you measure along the row now. At the beginning you will have, what will you measure? Lots of soil and a bit of plant. So that will give you a coefficient of variation that isn't that high. Then what do you get?
More plants.
Yeah, you get more plants, so you get like half. So you increase your coefficient of variation because you've got plant soil. So we have 3 treatments with significant higher spatial variability. So I was saying, you've got periods of drought stress increasing your variability. You've got, these treatments have general low soil quality, low soil moisture, that means stress, and they've got higher variability. Okay? This is what Bram showed you earlier, I think. Soil quality results. PCA analysis, no? I suppose you did because this is soil structure, this is topsoil resistance. Where do we see the soil? What can you say about zero tillage remove? This is an example from irrigated conditions. from a long-term experiment with 5 different tillage through treatments. We've got conventional beds, we've got 4 types of permanent beds. Permanent beds burn the residue, remove the residue, retain part of it, and retain all of it. And we've got different levels of nitrogen. Okay, what do you see from this one? Thinking about high stress, high variability. What we had here in terms of soil moisture, because here we have rain-fed conditions, and we've got irrigated conditions. That means that you control one of your factors, like soil moisture. Can you see here? If you look at the nitrogen treatments, which one has the highest variability? Yes, that's the, in terms of tillage treatments. Okay, so permanent beds, permanent has a higher variation. What can you tell me about soil quality in permanent beds burning your residue?
It's worse.
Yeah, it's worse. I'm sure chemists told you a lot about CA in irrigated conditions. I'll show you some results. So we've got bad soil quality, high variability. Next question, do we have different patterns in plant performance under different managements? And if we do, which soil factors are going to determine those patterns? Again, result from here, from central Mexico, from D5. This is a map of D5. You can see that I've made some of the plots white and other ones gray. That's because the treatments in D5 are divided in 2 big groups, the static treatments and you've heard that term, the more variable treatments. We've concentrated this one on the static treatments because it was a lot of work, so we just had to choose, and we only did so, not the intermediate treatments, only, so just conventional tillage, zero tillage, keeping, removing everything, and the 4 rotations. Okay, and why have we done this? Because our coefficient of variation is telling us that we have a certain amount of variation in the field, but it does not give us any idea about what pattern that variation is following. So we wanted to look more into detail at the pattern. So we made a map first of, to make this map we measured for maize all rows except for border rows. For wheat, we did 6 measurements along the field. So we had a pretty tight, pretty good distribution of our measurements. Okay, let's see what you see in this map. There's some plots that have something that the other ones haven't. If you look very carefully, this is NDVI going from low, the more yellow values, to dark green, the higher values. If you look carefully, it's easiest if you just start this way and you go and you look and you think. Now first, this one is a beautiful picture. This is the zero tillage remove one. Maize after wheat. This is maize after wheat, zero tillage, keeping the residue. People who don't believe in conservation agriculture, we always take them to D5, to this border, and I will say, look, remove, keep. 2 or 3 tons depending on the crop of difference, just keeping your residue. Now, when we can't take them to D5, I can do it with this one. And this one also explains why are we interested in spatial variability. Because spatial variability within your plot means here that you're losing like half of your plot when your plant performance is under the potential that it can reach. Clearly, because the plot next to it has got a lot higher plant performance throughout the plot. So this part that is causing your high coefficient of variation and your high variability, this part should be able to reach the same potential. Why isn't it? So that's why we're going to look what we are going to look at in more detail. Now this was zero tillage remove, zero tillage keep. This is maize in the same field repetition with conventional tillage. Now as you can see, we've got a little bit more variation. We've got a bit lower values, less darker green, but it's not as worse, of course, as zero tillage. removed. Now, this is something to look more into detail at spatial variability in your data. It's called a semi-variogram, and it gives you the degree of dissimilarity as a function of separation distance. Separation distance being between measurement points. Now, if you want to calculate your semi-variogram value for a certain separation distance, let's say for 1 meter, you look at all the points that have a separation distance between of 1 meter. You're going to calculate the difference between those couples, and you take a sort of quadratic variance, no? So this will give you a variance of all the measurement couples that have certain separation distance. Now you can do that for all possible separation distance, and then you get a semi-variogram. So this is the lag distance, it's called the separation distance between your measurement curves. And this is your semi-variogram value. Now, a normal semi-variogram has got this shape. So you've got points that are close together will be more similar than points further apart. At a certain point, which is called a range, a certain separation distance, if you go any further apart, your variance will not increase the difference between your points, because points will be independent from each other, and you reach a value that is just the population variance. Can everybody follow that more or less? More or less. So what you make from this is the easiest way to remember it, is the degree of dissimilarity as a function of separation distance. Points, if you've got spatial dependence in your data, you get these points closer together, will be more alike, and have a smaller variance than points further apart until you reach your population variance. If you don't have any spatial dependence in your data, you will just have this at your population variance. Okay, so this was what we thought they would look like, our different semi-variograms. I was saying we were looking at this now. This plot is zero tillage remove, and we've got a clear trend from low values to high values. Now that means that if you take points farther apart within these plots and you increase your separation distance, your variance will only get larger. You will never reach this plateau. So that's why we expect it to look like this. Now, zero tillage keep, we see a lower population variance, so we expect this to be lower than in conventional tillage. Okay. Now, these are the results. This is for zero tillage remove, the same plot that we've seen earlier, always number 17. So we see that we've got a beautiful right that is telling us, yes, we've got a trend. Now, that we had a trend, we already knew that. So if you want to see the variability you've got apart from the trend, you can just fit the trend onto your data and then subtract it. And then you remain with the variance that with the variability that you have superimposed on that trend. Do you see that? I just fit it. This now. We've got, this is the large part of your plot, this is the NDVI. We've got something like this, what we've seen earlier, so I've just fitted this onto it, and then you remain with what you've got from variability superimposed on that trend. Yeah? Okay, and now I made the semi-variograms for all that I was left with. This is the zero tillage remove, zero tillage keep, conventional tillage remove, and conventional tillage keep. It's all for maize. Now what the interesting thing is that you see that zero tillage remove, apart from that trend, it showed also the same variability as the other ones. And you see more or less the same type of same variable. If you compare this to the one before that we extracted, this is just an easy one. What we've got here is the sum of two of those easy ones. We've got one that goes like this, and then the second model that goes like this. So we've got two different ranges. The range of your first model and the range of your second model. Now the range of this first model is about 40 centimeters. And that you have two models is saying to us that we've got two different kinds of spatial variability. We've got a process that controls spatial variability with a range of 40 centimeters. And we've got another process, or the same process on a different scale, that is controlling your spatial variability on much larger distances. Now what is causing this, I don't know, because I don't have any data on that scale of 40 centimeters, because you would have to do a soil quality analysis on a very small scale, and well, we've just never gotten to that. So for that, if you have any ideas, you're welcome to tell us what this would be about. For this, we do have some data. We did, as I'm referring to the questionnaire, we did a soil quality analysis at 8 points within each plot. And then we made maps that are actually the color not really bad. I'll just show you. I don't know if you can see better. It goes from yellow. From yellow to green is always the low ones are yellow white, the high ones are darker green. This is plot 17, this one, the zero tillage remove one. This is the NDVI map that you've seen, and I've put now moisture time to pond for infiltration. Mean weight diameter from dry seed infrastructure and organic matter next to it. So what do you see? Yeah, so you've got the same trend in moisture infiltration structure and organic matter, from low values at this side to high values at that side that you see in the NDVI. Okay, why would that be? Any ideas? This is the side, was the bottom of the map, this is the upper side of the map. So we've got a very small slope in D5. I don't know if you've noticed it, because it's a small one. So it goes from this side to the other side. Okay, so what do you get when you've got zero tillage remove? What have you seen about soil quality, about aggregation, structure, infiltration, time to in zero tillage remove?
Well, if you have zero tillage remove, you have first, of course, you have erosion. You have erosion, and your soil aggregates like destroyed because you keep the physical barrier on the soil.
So you don't have any protection by mulch cover? You've got a bad structure, so when it rains, it just runs off towards those points. So you get an even greater lack of soil water. At the upper side of your plot, you get a lower NDVI and plant performance, lower biomass and yield production. That means that you've got less organic carbon left in your field, your structure deteriorates, your infiltration, so on and so forth. And at the other side, enrichment.
I have sedimentation already from the slope, but 0.3%. Maybe low, but there will be more water.
There will be more water left, so you don't. The degradation of soil quality that you get on this side will be smaller on that end. So in comparison, you've got more soil water, you've got higher plant performance, higher biomass production, structure integration. So if you do this, like we did in D5 for more than 15 years, you create, by your management, you create spatial variability in soil quality in your plot. Doing that creating that variability in soil quality, you create variability in plant performance. So we've got two different causes of spatial variability within your plot. We've got this variability in soil quality caused by management, and we've got that other cause of spatial variability that I talked about in the first presentation. That was stress. Okay. So when you do zero tillage, removing your residue, you get a general degradation of soil quality causing stress, so you increase your variability. Apart from that, what we see here is that you don't only cause a general degradation, you cause it at a different rate, a different amount on different places in your field, so you create extra variability in soil quality that is generating variability in plant performance. So this is zero tillage remove again, some other maps of electrical conductivity, sodium and inorganic nitrogen. What you see from these ones is that you get exactly the opposite trend. No? As I said, we... you don't have local filtration here. That means that your electrical conductivity is going up because you don't have any, well, your leaching is less enough. Your plants aren't grown, so they just leave the nitrogen fertilizer you give them in the soil because there's no water to bring into them so that they can grow. Okay, so we had planting plant performance following the trend in soil moisture, in filtration, in structure, and in organic matter, opposed to the trend in electrical conductivity, sodium, and inorganic nitrogen. That means that your water is the limiting factor here. You can do the same and get as an outcome that your nitrogen is the limiting factor of water. Okay, this is zero tillage keep, more or less the same maps. So this is plot 18, the one we saw with next to the 17 one, zero tillage remove one. This one has got a uniform and high plant performance. You see high moisture, infiltration, good structure, and since your plants are growing well, they need less nitrogen in the soil. This is conventional tillage. If you compare it to the zero tillage, what you will see.
How you do the measurement?